Yeah. Lecture 13. Let's do a few questions from the handout. We did question 1 last time, so this is question 2. So here you want to rent an unfurnished 1-bedroom apartment in Boston next year. The mean monthly rent for a simple random sample of 25 apartments is advertised in the local newspaper is 2,100. And assume that the standard deviation is known to be 220. Oh, I've been going around saying that you use t-distribution because number of samples is less than 30. But here's a important problem here. Assume that the standard deviation is known to be 220. So this is actually a very important information for us because this is saying that you know the standard deviation. Yeah. I don't know how. Maybe there was some bigger census in the previous year or something. But let's say that the standard deviation is known. Okay. In that case, which one do you use? Inverse t or inverse norm? You use the inverse norm in that case. Okay. Right. So yeah, I was talking. So there are 3 cases, right? The first case is when your sample size is less than 30 and the standard deviation is not known. In that case, you use inverse t. You use the t distribution. Okay. However, the other 2 cases are when the sample size is bigger than 30, or still another case is maybe the sample size is less than 30, but your standard deviation of the population is known. That's a more rare kind of situation, but if for some reason it is known, then you can still use the normal distribution despite the sample size being less than 30, right? Okay, so sorry about that. I've been going around and telling you to use an inverse t distribution because 25 is less than 30, but it doesn't work like that. Okay. All right, so let's try this. We first need to calculate the margin of error, right? Solution. You have to do margin of error. And the formula for the margin of error is the critical value times what? Sigma, the standard deviation, divided by square root of n, right? Yeah. And for this, you need to first find out the z alpha over 2, the critical value. I don't like it that way. Okay. And that's calculated by using the inverse norm because of what we just discussed, rather than inverse t. See, if the wording was that the sample standard deviation was 220, then we use the t distribution because that 220 is just from the sample. However, the wording here is that assume that the standard deviation is known to be 220. That indicates that your population standard deviation is somehow known to you. Okay, that's a rare case, but for some reason, let's say that that's known. Okay. All right. So inverse norm, you put 1 minus alpha over 2. But what is our alpha? 1 minus confidence level is your alpha level, or it's also called the significance level, right? So your significance level is 0.01. So you put that 0.01 divided by 2, you put it there. And let's see what that gives us. Let's go to the calculator on second vars, go to inverse norm. You can also use your table. We have something in there. I just have to change this one to 1, and that's it. Let's enter, enter, enter. And that gives you 2.576. That's 2.576. All right. Okay. So now we have the margin of error as 2.576 times sigma, which is 220, and divided by the sample size, which is 25. And that's equal to, let's see, 2.576 times, oh, that doesn't work. Okay. Times 220, and then divided by square root of 25, and then enter. And you get 113.344. 113.344. Yeah.
So if we were to use t-distribution,
Yeah.
that would just tell us the z alpha over 2. So it would do the same thing inverse norm does, but if we didn't know
So
the
so
standard deviation.
so if the wording was, the question is, what happens if we use a t-distribution? Well, if the wording was that if the sample standard deviation is 220, then you have to use an inverse t-distribution. And for that, you don't call this as z alpha over 2, but you call this as t. Okay? But you do the same thing. It's inverse t instead of inverse norm. And for the inverse t, you also have to provide the degrees of freedom, which is 25 minus 1. And you get a different value, which is higher than this number. So using inverse t gives you a wider confidence interval. Right? Okay, so let's just round to the nearest sense, and that's what you have. And therefore, the confidence interval is mean value minus this, right? So I'll just write it like this, minus 113.34, and then the actual population average is between here to plus 113.34. Okay, it's minus E and plus C. Did somebody calculate this? Yeah.
What is mu?
Mu is, well, I got lazy. Mu is what? Is this thing. Population mean. All right. Yeah, you should actually know how to read this. Okay, Greek letters, you have to know how to read them. Okay, this Greek letter is spelled as mu. That's mu. This Greek letter right here is spelled as sigma, pronounced sigma. You should know them. All right. So what are the numbers? 1996. No, 1986.66. Right. And 2213.34. So that's the answer to the first one. Yes?
I'm still a little bit confused as to why you used inverse norm instead of inverse t.
You're still asking me why you use inverse norm, inverse t. So let's review. So when to use inverse t versus inverse norm. So let's make a table. 3 by 3. So I don't like this table design. No, I don't like. Oh, first column. All right, good. That's better. Let's use this. All right. So sample less than 30 and sample bigger or equal to 30. And the other case is population STD known and population STD unknown. Okay. So what does the t-distribution do? Why do people use a t-distribution? That's because usually when you have a sample and you're trying to deduce the confidence interval, you commit the sin of using your standard deviation of the sample as a replacement for the population standard deviation, okay? Because normally you don't know the population standard deviation, okay? Only for very rare cases you do know, right? And that causes additional uncertainties, which makes the bell curve look wider, right? That's basically the point. The t-distribution is something that, a distribution that looks like a bell curve, but it's wider, right? So therefore, what I'm saying is that the t-distribution is only applied to the case when population standard deviation is unknown. So that's when you use t-distribution. But if your sample size is big enough, then you use the normal distribution, because the sin of using the sample standard deviation as a replacement for the population standard deviation is not so bad. Okay, if you have 30 sample sizes, your standard deviation estimation from your sample is probably pretty close to the population. Yeah. Wait. Okay. So that's when you do it. But if your population standard deviation is known, then you don't have to worry about this. It's always use the normal distribution. Okay. So in this previous question, the standard deviation is known to be 220. That's the case when you have this first case. So regardless of whether your sample size is less than 30 or more than 30, you just use the normal distribution. Get it?
Yeah, but that brings me to another question. So then, what would we plug in like SX in the formula? Like T alpha over 2?
Oh, no. So population standard deviation is known, then we use, so here we use the population standard deviation.
Okay.
Okay? But if it's not known, what do? We use the sample standard deviation.
Okay. Oh, I see. Okay.
Because you don't know the population, so you just use SX as your replacement for the sigma. Okay, your question.
If we have to use inverse t, we're using this formula to find the standard deviation every time. If we're using inverse t.
No, that has nothing to do with being inverse t.
What do you mean?
This is
yeah, but like for this, it says.
No, you're just being confused with two things. I just gave that formula is for finding the sample standard deviation. Okay. Yeah. All right. So hopefully that clarified things. Let's look at the next question. Data analytics company performed a nationwide poll of 2011, randomly selected 13 to 7. I don't like this. That randomly selected 13 to 17-year-olds. Of these 2011 teenagers, oh, I see. I thought 2011 was a year, but there are 2011 teenagers. Okay, yeah, that was confusing. All right. So a nationwide poll of 2011 randomly selected 13 to 17-year-olds. Of these 2011 teenagers, 309 of them had vaped in the past 12 months. Okay. Find the point estimate of. You have a question? Okay. Find the point estimate of proportion of people in this age group that vaped in this time frame. Okay. All right. So here, we see this new word, Point estimate, what's that? Point estimate is you're estimating the actual proportion, the population proportion from your sample, right? So you just get a single number. So this would be, since you have 309 out of 2011, that's your point proportion, okay? So maybe I should make a note here is that point estimate is p hat, okay? Or the x bar if the question is regarding the mean value. Okay, so here the point estimate is the p-value, not the p-value, the proportion you get from the population. Okay, so since 309 teenagers vaped out of 2011, let's see what that amounts to. 309 divided by 2011. Sorry to change that division. Okay, enter 0.1537 or 15.37%. Okay, so from this sample, 15.37% vaped. Okay, so that's our best guess, right? We don't know what's going to be the true value of population proportion if you selected all the teenagers between 13 to 17-year-olds in the United States. Okay, that will be probably different, but assuming that our sample is good, meaning that it's close to a simple random sample, then this should give you a pretty good idea of what the actual proportion is, right? So this comes with margin of error. So let's find the margin of error. Now for the margin of error, let me erase this much. Margin of error of the proportion is given as E equals to Z alpha over 2 times square root of p hat q hat over n, right? Is that the right one? PQ over n, right? Yeah, it's this one. Okay. All right. So that's what we have, and therefore, well, you still have to find z alpha over 2 by doing the inverse norm. But I happen to remember that value. It's 1.96 for 95%, and then square root of p is 15 or 0.1537, and then 1 minus 0.1537 would be 0.8463, and you divide it by 2011. No, this doesn't look like that. All right, that's fair. Okay, so you see that Q hat is 1 minus P, so that's why I put 0.8463. I think I don't need to show you why I get 1.96 because in the previous lecture, we've already computed the confidence interval, the critical value for 95% confidence level. So that's it. Let's plug in the numbers. 1.96 times square root, and let's open a parenthesis to make sure that all of these numbers are inside the square root. So 0.1537 times 0.8463, and then divide by 2011, and you close the parenthesis, then enter. and you get 0.0158. So that gives you, all right, so that's your margin of error, which is like 1.58%. Okay.
Can you show how you got 1.96?
You want to see 1.96. Okay. So it's 95% confidence level, right? What's the significance level?
You do 1 minus the CL?
Yeah. So what do you get?
What, 0.05?
0.05. And then what do you do to find the critical number if it's Z? Second vars, right?
Yeah.
Inverse norm. 1 minus alpha over 2. So you put 5 here, right? Right? That's 1.96, right? Okay, so you use this, and you have to add or subtract this. So the answer would be 15.37 plus or minus 1.58%. Yes?
Where did you get the 0.8463?
0.8463 is 1 minus, so let's put a note there. Note Q hat by definition is what, 1 minus P hat, right? P hat, which is 1 minus 0.1537, which is 0.8463. Yes?
So when you write 15.37 plus or minus 1.5,
8%. Yeah.
that's another way of writing the confidence interval?
Yes, that's a good question. Thank you. The question is, I wrote like this. Is this another way of writing the confidence interval? Yes, that's another way people write confidence interval. What does this really mean?
That would be correct.
That would be correct. So what does this really mean? It means that the actual proportion is between 14 point, what is it, 5.279%, okay? And if you add it, it's 16.95. Right. So although we do not know where the actual proportion would be, you know that with 95% confidence, it's like I'm 95% sure that the actual value is between 14.79% to 16.95%. Yeah, that's what it's saying. All right, now off to a new topic today, hypothesis testing of mean. Now we're going to do something similar next class, so I'll be rather brief with the calculation this time, okay? So, the problem is like the following. If there's a claim about the mean value about a population, how can you judge whether it is correct or not without taking the census of all data? Yes?
Will hypothesis testing a mean be on the quiz on Wednesday or just estimating population?
The hypothesis testing is not on the quiz on Wednesday. All right. If there's a claim about the mean value, how do you know whether it's correct or not without taking the census of all data? Well, we use sample because that's all you can do, right? Usually it's not feasible to take census of everything, and it's time consuming and takes money. It's good to have an example in your head to follow this reasoning. So remember in the last lecture, we had the question where, maybe it was the one before, we had a question where a vendor, a grocery store bought some, was it pumpkins, maybe? Was it apples? Pumpkins? Okay, so it was trying to buy some pumpkins from a farmer, and the pumpkins were like they were coming in boxes, and they were claiming that their pumpkin size was like certain pounds, 30 pounds or something. And the grocery store wanted to verify that, so what do? They open a box and weigh all the pumpkins and see how much they weigh, right? And by doing that, they can figure out whether the farmer, was lying or not, right? So that's the kind of questions that you want to resolve. And this is actually pretty important when you're running a business. I mean, you don't want to be shorthanded by some other uh, other people who's providing the materials or other services, right? So often you want to do some quick sampling and make a quick judgment whether you're getting what you're promised, right? Uh, and it would be nice if you can figure out or spot the lie by using statistics. And the idea is to do this. Take a simple random sample from the population, or open a box of the pumpkins and weigh them, right? You get the raw data, and then calculate the mean. And if the mean value is very different from what you're promised, then you say, hey, I don't believe what you're saying. You go back to the supplier and say, hey, I don't believe what you're saying, so the deal is off, okay? And that's a very smart way to run a business, okay? If you are ever trying to run a business, okay, or if you want to be uh, working as a manager in a big company, right, vice president, and you want to make smart decisions, right? You want to ground your decisions on statistics. Yeah. That's how you can get promoted and bring profit to your company, right? All right, so it's a good idea, but the problem here is you end up with this question: how much difference is big enough to say? How much difference is big enough to warrant that the original claim is wrong, right? You need to know that, right? Or else doing just calculating the mean is not going to give you anything, right? And so that's what this hypothesis testing is. And let me outline the 4 steps. So actually, the 4 steps I'm outlining is a very standardized type of steps. So in some exams, you might see the question appearing as like, follow the 4 steps in hypothesis testing. And then you have to show all the work shown in these 4 steps, all right? So let's see. First, you have to form a pair of hypotheses to determine the claim. And here are 2 important words. One is the null hypothesis, and the other is the alternative hypothesis. And the null hypothesis is what the supplier is claiming. Our pumpkins are 30 pounds. That's their claim, right? However, you're suspicious, right? And you want to test the claim by producing an alternative hypothesis, okay? And contrary to the confidence interval calculation here, you have 3 different types of alternative hypothesis, and that's what makes this slightly more challenging than the last one. And you have left tail, right tail, and two-tailed. Now, we're going to go over some examples today to better understand what these are. But to give you some idea of what this means, it's like the following. So often when your supplier claims something, there are cases where you don't care if it's above. So if the farmer claims our pumpkins are 30 pounds and actually their average is 31, you don't really care. It's better for you. You're getting better, bigger pumpkins. Let's say they sell for more. Okay, so let's say if it's 31 or 32, you like it. It's not a problem, right? However, you're worried that they're selling you the smaller ones. If it's 29 or 28, then you don't like the deal. So deal is off, right? So what you do is you start with the null hypothesis and then think about the alternative hypothesis. And the question is this too low? Is the value too small from the claimed one? In that case, you call this the left tail test. Now, when we do the examples, you'll kind of see why it makes sense to think of this as a left tail test. So if you don't fully understand right now, don't be too alarmed. But that's basically the idea, right? Or sometimes you might be worried if the value is too low, then you want to prove that, oh, this is abnormally high. Then you would use the right tail test. And if the question is simply, is it equal or different? In that case, you use the two tail test. All right, so it's a competition between the two hypotheses. And you start with a null hypothesis and just go through the statistical testing to see if it all makes sense or not. If it doesn't make sense, if the values that you get is doesn't agree with the null hypothesis, the idea is to reject the null hypothesis and choose the alternative hypothesis. That's the overarching approach. But the first step is first identifying the null hypothesis and alternative hypothesis. And therefore, in all questions on the exam, you have to first start by stating what the null hypothesis is and what the alternative hypothesis is. And in all cases, the null hypothesis is written as the average equal to the claim value. That's always how the null hypothesis is written. Yes?
The null is going to be given to you.
No, well, it's a word problem, so the null is not going to be explicitly given to you. You have to figure it out. But it's usually there's a claim or there's a preconceived idea that the value of the mean should be this value. It's given, okay? So you write it as equal. And then the alternative hypothesis, you have to choose whether to say it's not equal or it's less or it's more. So those are the things that's more challenging, okay? So null hypothesis is easier to figure out. Alternative, you need a little bit more thinking. All right, step 2, what do? Well, after you figure out whether you want the two-tail or the left or right, you have to draw the normal curve and shade the region, okay? And this shaded region is called the rejection region. I should write that. Shade the direction of H1. This is called the rejection region. Okay. Or sometimes, or just RR. Okay. So if you read some question and sometimes they just say RR, that just means rejection region. Okay. With a desired significance level alpha, significance level is 1 minus confidence level. Then find the critical value of the region. Yeah, so you have to find the critical value depending on which test you're choosing. Now the two-tail, we've seen this many, many times, right? So that's not surprising. However, the one-tail left and one-tail right, so for the one-tail left, the entire region is on the left side. And because the area of the shaded region should add up to alpha, just inverse norm of alpha will give you this critical value where that's the boundary of this shaded region, okay? On the other hand, if you have one tail right, it's going to give you, you have to do inverse norm of 1 minus alpha, which gives you this boundary on the right side. And if you put numbers on there, it kind of makes sense because if, let's say your significance level is 5%. So you're thinking of this shaded area as 0.05. Then what's the unshaded area's area? That's unshaded region's area is 0.95, right? And therefore, you have to do inverse norm of 0.95, which will give you this boundary where it divides the two regions. Okay, now step 3, you have to compute the z-score or the t-score depending on the sample size. This is called the test statistics for the mean. So sometimes you might be asked, what is a test statistic? That means you have to show the z-score. Another name for the z-score in this context is the test statistic. And you either use the z-score or the t-score. And you can see that these formulas are basically the same thing, except that if the sigma is known, you use the sigma. And if the sigma is not known, you just use Sx as your replacement for the sigma. Okay. And then step 4, compare the test statistic with the critical value. If the test statistics lies in the shaded region or the rejection region, then the null hypothesis is rejected and the alternative hypothesis is chosen. Otherwise, the sample is not statistically significant to reject the null hypothesis H0. All right, so that's the overall idea, and you probably wouldn't understand what this is saying unless you see an example. So let's go to our first example.
Wait, can you go back to my notes? Oh, cool.
Yeah, this is all in the notes. Okay. All right. All right. All right. So example 1: a company is buying 25-ounce wine bottles as gifts to give away at an annual event. However, the wine did not seem to be 25-ounce, so they took 10 bottles and came up with a mean value of 24.3 with a sample standard deviation of 0.9 ounce. Use the 0.05 significance level to conclude whether or not the average fluid volume of the wine bottles is less than 25 ounce. Right. So here you're worried that you're getting wine bottles that doesn't have the claimed amount of wine, right? And you're losing money, so you don't like that, right? So what do? Think about the null hypothesis first. What's the null hypothesis? Remember, the null hypothesis is always equal, right? So think about the what's equal here. You want to test whether the wine bottles have the fluid of 25 ounce or not, right? So you put equal with 25 as your null hypothesis. Does that make sense? This is actually an important point, okay? If you are not following, you should really pay attention to this point, okay? You write down the null hypothesis as equal sign, and therefore you read the question and say, oh, we're trying to test whether the bottle is less than 25 or not. So you say mu equals to 25 as your null hypothesis. All right? Okay. So now let's move on to the next one, which is the alternative hypothesis. Here, the important word is you want to test if it's less. Okay? You want to test if it's less. You're suspicious if it's less. You don't care if it's over. That's not going to be a big problem. Okay? Yeah. You're getting more for the same amount of money, so you don't care. Okay? So that's why your alternative hypothesis should be mu less than 25. Remember, there are only 3 choices for the alternative. Either mu not equal to 25, mu bigger than 25, mu less than 25. So it's a multiple choice question. And you choose a mu less than 25. Why? Because you want to show it's less. Okay. Yes?
Is it mu not equal to 25, also mu is less than 25?
Oh, so the question is, isn't mu not equal to 25 also mu less than 25? One direction is true. If mu is less than 25, then it is true that mu is not equal to 25. But mu not equal to 25 doesn't mean that mu is less than 25. It could be over. So these 3 statements are, some of them includes the other, but you have to distinguish them depending on which one the question is asking. Does it say less, or does it say more, or does it say different? Okay, so those are the keywords that you want to look for in the word problems, right? Okay, you still have a question? No?
I was
Oh,
gonna say,
okay.
what is the question
All right.
phrase?
So the keywords that you have to look for is less or more or different, not same, something like that, okay? So here it says less, so it must be less, okay? Now that means you're looking at, so the red zone, maybe red zone is another nice way to say the rejection region. So the rejection region is when it's too small, right? So that's why you shade the left side. That's why this is a left tail. Is that good? Yes.
For the two-tailed, the question would be question not equal to, right?
Yeah, the question was for two-tail, the alternative hypothesis will be not equal, and that's correct. Okay, so so if the wording says it, the wine bottles is instead of less here, if it says not equal to 25, then you use mu not equal to 25. Right? Okay, but this initial step is very important because if you choose the wrong test, your conclusion becomes different. Okay, you don't want to make that mistake. So you really need to make sure that you get the null hypothesis and alternative hypothesis right, because if this is wrong, everything you do afterwards is wrong. So you don't want to make that mistake. All right, so let's continue. Our significance level is 0.05, right? And since the population standard deviation is not known and the sample size is less than 30, we have to use a t-distribution, which requires the degrees of freedom calculation. Degrees of freedom is always n minus 1. So our degrees of freedom is 10 minus 1 equals to 9. All right, let's continue. So we now have to calculate what is this boundary, right? And I know that this area should be 0.05 because that's the significance level. So we look for the inverse t. So you go to second distribution, you go to inverse t, or you can use the table. I like using the calculator. So you do, instead of doing 1 minus alpha over 2, that's for two-tailed. See, I just need to know what is this value if the left side of that value has the area of 0.05, right? So you just need to put 0.05 here. Degrees of freedom is 9, and you paste it, and that gives you negative 1.833. Okay, so that's how you get this value. And then the t-score that you get, you just need to know how off your 24.3 is from 25. Remember, we're trying to judge whether your sample mean and the actual claimed mean is a lot different or not much different, right? So that's why we take the difference between the two, and we have to kind of rescale it by using this standard deviation, also divided by the square root of n. Doing that, it gives you negative 2.45. So let's think about what that means. See, this boundary right here, what's its x coordinate? Can somebody tell me what this boundary x coordinate is? Maybe I should copy this and. Okay. So, what is this point right here? Right here. It's negative 1.833, right? It's so hard to write here using a mouse. Okay. However, our test statistic came out to be negative 2.5, right? So is negative 2.5 left of this boundary or the right side of the boundary? Left, right? So this is the negative 2.4 should be somewhere here. I'm not going to write it. Let's say negative 2.4. Okay. So that is inside the rejection region. Okay. If your test statistic belongs to the rejection region, then what should you do? If it belongs to the rejection region, you reject. Okay. So that's the next step. because your test statistics is in the rejection region, the null hypothesis is rejected, and you adopt the alternative hypothesis, which says what? What's the alternative hypothesis? That the wine is less than 25 ounce, right? And you go back to the company, hey, you sold us wines that were below 25 ounce, okay? We have proof. Right? And actually, these kind of arguments can hold up in court as well, right? So if there was like a contract written previously, right, then you can actually take that supplier to the court and get money. All right, let's try this second example. You have a question on this one? Yeah, I thought you said, okay, fine. All right, let's look at the second example. A frozen food manufacturer has been making dinner packs, assuming that the average adult male consumes 2,500 kilocalories per day. However, they're not sure if this has changed recently. Actually, it changed a lot. We consume more like 3,500 calories per day, or even more, right? But let's say this was like done in the 80s or something, when people were eating just right, okay? All right, so they measured daily calorie intake of 50 adult males and obtained an average of 2,655 calories and sample standard deviation of 280 calories. Use 0.01 significance level to conclude whether or not the average adult male's calorie consumption has changed. Because, you know, for this company, the worry is not whether the calorie increased or decreased. Either way, if it changed from your basic assumption, then probably the customer base is now changed, and you have to change your the menu according to that. You might have to make the portion size bigger if it's a bigger change, make the portion size smaller if it's a smaller change, right? So in this case, you're looking to see whether it's different, not less or more, but different. Yes, you have a question?
So, from what point in the question
Mhm.
do you figure out your null hypothesis? Like, what?
Okay, the question is, at what point do you figure out null hypothesis? All right. So how do you figure out null hypothesis? Remember, it's always the null hypothesis is something equal to something, right? And look at the last. Usually, it's in the last sentence. Okay, look at the last sentence, and what is it saying? It's trying to test whether there was a change in the adult male calorie consumption, right? So calorie consumption is the quantity that you're trying to figure out, right? However, the actual number of the adult male calorie is not listed here in the last sentence. Sometimes it is given, but here it's not given. So you have to read the entire question and see where it has the adult calorie consumption. And here, 2,500 calories is here. Another one is 2,655 calories, right? So you have two different competing numbers. Which one do you think is the right one? It's the 2,500 because it's the previous claim. Okay, 2,655 is the new value obtained from the sample. That's the one that you use to draw a conclusion, right? But the previous claim is the 2,500, the original value, right? So although sometimes the questions might be worded in a different way, but usually the first number that appears for that quantity is the value to take for the null hypothesis. Not always, but usually.
And also, since the standard deviation is known, it's inverse norm.
No. Here, the population standard deviation is not known. Only the sample standard deviation is known. However, 50 is bigger than 30, so it's inverse norm. Okay. Any other questions? So you got my point? The question is about adult calorie consumption. And because the adult calorie consumption, the previous value that's assumed is 2,500, you want to use mu equals to 2,500 as your null hypothesis. All right. Next, now alternative hypothesis should be mu not equal to 2,500 because, as I explained, you're not just worried whether it's less or more, but either change will lead to your change in the company's approach, right? So that will require you to have a two-sided or two-tailed hypothesis testing. Okay, so alternative hypothesis is two-tailed. Right. So this is a two-tailed test, and the shading should be in both cases. And it means that the sum of both of these areas should be equal to the significance level. In our case, the significance level is 0.01, right? So I shade it like this, but the actual shading is much smaller, further to the right, further to the left, okay? All right, so let's try that. Once you have the significance level, you can now calculate the critical value as 1 minus 0.01 over 2, just like how the table in the other page of the handout states. So you have to use this, and you get 2.576. So this boundary right here is positive 2.576. This left boundary, because of symmetry, this is negative 2.576. Okay, so be aware that those are the boundaries of the critical region, the rejection region. Now let's calculate the test statistic. Now, if you calculate the test statistic, you get 3.914. So where is that at? On the far right. That's very big, actually. On the far right, right here, right? So that is indeed in the rejection region. If it's in the rejection region, what do? You reject the null hypothesis and you adopt the alternative hypothesis, and your conclusion is, yes, there was a change, okay? That's how you can conclude. All right, we only have 5 minutes, but let me really quickly go over to the last one, because this is an example where that you don't reject, okay? All right, so example 3. So here, let's say population standard deviation is known to be 2.1. Sample mean of 10 samples is 13.5, whereas it is hypothesized that the population mean is 14.2. Use 0.01 significance level to decide whether the population mean is 14.2 or not. Okay, so since we don't have time, I'm going to skip all the step 1s through 4. However, you should know how to do them. So step 1, you have to write down the null hypothesis. Okay, what's the null hypothesis? Mu equal to 14.2. Okay. Now, what's the alternative hypothesis? Mu not equal to, because it's equal or not. Okay. So we're worried about whether it's not equal. Yes.
Where'd you get the 12.8 from?
12.8? Oh, 13.5. Sorry. Let me change this one. I think that I made a mistake there. I think this should be it. All right. Okay. So if it's 12.8 is the sample value, now because it's a two-tailed test, you again get the 2.576 as the previous example. But here, the important thing is when you calculate the test statistic, the z-score, you get negative 2.10, and that is not in the rejection region. And the important thing I want to state here is that there is insufficient evidence to state that population mean is different for 14.2. So the important thing I want to say here is that when you fail to reject the null hypothesis, you don't say that therefore null hypothesis is true, because we don't know. Only when you can reject the null hypothesis, you can say, oh, with 95% confidence level or 0.05 significance level, we can reject it. Okay. But when you cannot reject the null hypothesis, we don't say that the null hypothesis is true. You just say there is insufficient evidence to state that population mean is different from 14.2. So that's the thing that you have to know. Okay. Thank you.